everyone. So today I'm going to be presenting a model of a human life based on some aspects of quantum mechanics and condensed matter physics. I want you all to remember that humans evolved on this planet and we fit the constraints of our world that's based on classical mechanics. When I say classical mechanics, I'm talking about the reassuring confines of Newton's laws. The motion, the motion of a planet to the grain of sand. When I'm talking about dimensions that are set, that can be observed. These are observable dimensions. So a motion of a planet, a grain of sand that are at a finite temperature and that are at a certain speed, from stillness to below the speed of light. Anything else after that becomes non-observable, and new questions start to arise from that, and that's when we worry about quantum mechanical effects. Now, in the 1900s, some of these physicists became aware that there were some inherent missing points to the Newton's laws, and they developed a model based on the inherent mechanical, the nature of light being both a wave and a particle. So that is what the inherent spookiness came about for quantum mechanics. Now, the important thing about those kind of systems is a classical system is something that is actual. It's actually what's occurring here in the now and it's observable. A quantum system has potential, and it's that potential that it makes it a little bit more difficult to understand, and some of the questions about its nature arise. Potential versus actuality is something that's very important to keep in mind. Now, in this day and age, you don't really hear quantum mechanics when you discuss science of small things. You talk about nanotechnology. Nanotechnology is a very, very broad word that applies to all kinds of sciences: chemistry, physics, biology, etc. And what most people think of when they think of nanotechnology are perhaps machines that go through your body and clean it out, or that can create matter, when in fact that's not really the case. True nanotech systems have very low dimensions. Now I'm going to give you a little analogy here about sizes. I want you to envision the head of a pin, which is approximately 1,000,000 nanometers across. So if I was going to use a chemical system, say carbon atoms, it would take 6 to 8 million carbon atoms to go across the diameter of that head of the pin. So when I talk about nanotechnology, it's really about atomic level control. So those visions that you see of them little machines, those are much larger systems than what I mean. It's atomic level control. And we already have that manifested in our lives today. We use superconductors, quantum computing is being developed, microscopes, shielding technology. These are all things that are used every day and based on the principles of quantum mechanics. And that is important to keep in mind, that it's a continuously evolving system. So nanotechnology is also one of the founding principles that uses what's called the Heisenberg uncertainty principle. And most people, when you say Heisenberg, they think of Breaking Bad and Walter White. So he was the Walter White of physics. And all he's trying to say is that you cannot simultaneously measure the position and the momentum of a particle with any kind of high precision. You can't know one or the other at the same time. So this has to do with the discreteness of electronic states and the confinement of electrons. And that's all that really means. You're going to confine these systems, but you still can't know the exact motion of the electron. So with that in mind, condensed matter physics study low-dimensional systems, and these systems are based on the confinement of these electrons. So if I have a three-dimensional system, the bulk electronic state is a big, smooth mass. Let's just use that for just to throw it out there. You take it step down. You confine it in one direction or more. You step down to a two-dimensional object, which could be a quantum well. So we confine it. The density of states for these electronic wave functions become a little bit more discrete. There's a little bit more trajectory to it, almost a stepwise. You confine it down another dimension to what's called a quantum wire or a one-dimensional system. You have what's called a peak system. So it's a series of peaks. You take it a step further down to what is called a zero-dimensional system, which is really another word for an artificial atom or quantum dot. You have discrete single-point energy states. Single-point energy states. Okay? That's really important. I want you to remember all of that because it's going to come up again. So now, back to the analogy of the uncertainty principle. Particle and wave behavior. Another good way to think about that is a wavy potato chip. You all know what that wavy potato chip looks like with the waves and the ripples, but if you break it up, you have a little piece. It's the same thing. A piece of the potato chip is still the potato chip, even though it's not part of the wave. So that's another way to think about it. So we're down at these low dimensions. We have different types of energy states. The beauty of these systems is they're so small and they're reactive different than bulk because of what's called an increase in the total surface area. So I have another way for you to picture this. I want you to all to picture a 1 centimeter by 1 centimeter cube. So the total surface area of that would be 6 cubic centimeters, correct? If we chop it up to 1 millimeter cubes, the total surface area of the system now goes up to 60 cubic centimeters. Now, take it a step further to nanometers, and we're going to have 60 million cubic centimeters of surface area. Now, why is that important? Very simply, chemical reactions occur on the surfaces more so than the core of these particles. So when I say particles, I mean a cluster. So the more reactive the surface, the more surface area there is, the more reactive it's going to be. That's where we're going to have these interactions of quantum mechanics that are going to occur. A perfect example of this is what's called the cadmium selenide nanoparticles. There's a beautiful famous picture in science that has a bunch of little vials that glow with a backlight into the formation of a rainbow. They're all the same particles, but why do they emit different light? Because the cores are different sizes. So the smallest one have the highest surface to volume ratio, much more energetically active, discrete energy states. Blue light is emitted. The larger cores, less surface area, less reactive, red light is emitted, and all in between depending on the size of the clusters. Now these clusters are important. They're going to show up in your new technology, your new smartphones, all kinds of things like that. It's going to be important. And science is continuing to work on that by studying surface areas. So surfaces are the magic. That's where the magic occurs. Now, quantum mechanics, it's the inherent nature of the wave-particle duality that causes a lot of mysticism to be developed, right? You've all heard about it. But true science follows the scientific principle. Pseudoscience does not. Quantum mechanics has a mathematical foundation that, while a lot of the buzzwords don't make a lot of sense, the foundation is there, and it's based on the improving of Newton's laws and the work of Einstein, Dirac, a bunch of other scientists that happened in the 1900s. So now, I want you to remember that when people throw kind of some pseudoscience jargon out there about it, it's just not. Remember the interaction of surfaces and the confinement of electrons, and you will have it. You will, I promise. So, a lot of scientists, like me and a lot of people I know, are kind of sci-fi geeks. We read a lot. We're into thinking about the future. And in the 1980s, there was an author named Werner Vinge who was credited with the first use of the word the singularity, which is that hypothetical time where computer intelligences might develop and then supersede the ability of all of humans. And that's the creation of the first artificial intelligence. There is a date that's akin to Moore's law that maybe 40, 50 years from now, it might happen. So in our lifetimes, we could have artificial intelligence. With that in mind, I like to think of my life as a series of discrete energetic states versus the bulk. The bulk is not really representative of all the nitty-gritty things in my life. For example, Facebook, I don't know if anybody Facebooks, everybody does. The girl on Facebook that I present is two-dimensional, and I wish I was as cool as she was, because she looks really good on the computer, but it's not really legit. If I break it down further to the discrete energy states that I can think of in my life, like interactions here or things that I wouldn't share on Facebook, there's a wealth of knowledge out there that could all be used to present my life. So I go from discrete, zero-dimensional, to three-dimensional bulk. So with all of that information in mind, I kind of think I would like the artificial intelligence to know the person that I am now, even if it's not going to be created for 40 or 50 years. If I save my information, I can share it. And I want to think of myself as these discrete states, that the sum of those discrete states combines both the benefits of a classical world and a quantum world. And with that in mind, all of you can think about that, and you can interact as discrete states, remembering all of your information and kind of archiving it almost. I don't want to say that, but just think about your life beyond 3 dimensions. If you reduce it down, there's actually more information there because your surfaces are more active. So a physicist named Dirac wrote a quote, I don't know how many years ago, but it says, if you pick a flower on Earth, you move the furthest star. Some people might see that as a pseudoscientific way of looking at things, or you can look at it as an interaction between the classical and the quantum world, where everything has a set of bulk states and a set of discrete states. And I, for one, can't wait for my artificial intelligence to know the person that I am now, even if I'm 80 years old when it's created. So with that in mind, interact and be electronic. Thank you.